Improper integrals deal with evaluating the area of an unbounded region. Now, typically, when you would be finding area, you would think of a fully enclosed region, such as the area of a polygon. Or, in the case of definite integration in calculus, you would typically think of the area of a region such as underneath the graph of the function y equals 1 over x from, say, 1 to 2, and you'd be looking at a fully enclosed region bound by the vertical line at x equals 1, the vertical line at x equals 2, and the graph of the function 1 over x, and the x-axis, so that we would have a fully enclosed region which has a definitive finite area. But what if the integral we are seeking to evaluate is not on the interval from 1 to 2? What if instead we are looking at the unbounded region underneath the curve extending outward forever with no right limit? Another way to write this might be the integral from 1 to infinity of 1 over x dx. Now, of course, the problem here is that this is an unbounded region. It extends forever. But, interestingly enough, that does not necessarily mean it has infinite area. In fact, depending on the function that we're working with, the area may actually be finite. Now, the problem, of course, in actually evaluating this is that we cannot actually reach infinity. But that is exactly what the purpose of a limit is. There are two types of improper integrals. The first that we will look at in this video deals with infinite limits of integration, when the lower and or upper limits of integration extends to positive or negative infinity. There are three situations that can occur here. First is that we have a function that is continuous on the interval from a to infinity, and therefore we integrate from a to infinity. The approach that we would take here is to actually replace the upper limit of integration with a definitive value, and then allow the upper limit of integration to approach infinity. So that we would evaluate the integral, the definite integral, in the typical way using the antiderivative and the fundamental theorem of calculus. But it would leave us with an expression in terms of the upper limit b. We would then apply the concept of a limit to that expression so that we could then see, well, what's going to happen as the right endpoint of this interval extends further and further outward. On the other hand, we may have an integral that extends leftward, that is unbounded to the left forever. In this case, we would take the same basic approach where we would replace the lower limit of integration, in this case, with a definitive value, or rather with a variable, and after evaluating the integral, we would then allow x to approach negative infinity and see what happened from there. The third scenario is what happens if both limits of integration go infinite, if it is unbounded on both sides. Well, unfortunately, we can only deal with one infinite limit at a time, but we have a property of definite integrals that says that as long as the function is continuous on the entire interval, then we can pick any place in the middle of the interval and separate the interval into two separate intervals. And therefore, we can integrate to the left side of that value and then separately to the right side of that value. So we can have a region that is unbounded to the right, to the left, or to both sides. Let's look at some examples, starting with the first example that we used, namely the unbounded region to the right under the curve of 1 over x. So again, we need to deal with the fact that we cannot actually evaluate the antiderivative at infinity because we can never reach infinity, but we can see what happens as the upper limit approaches infinity. So our first step is to replace the upper limit with a variable, and then after evaluating the integral, to take the limit as b approaches infinity. So let's start with the antiderivative. We can remove the concept of the limits of integration and just focus on the antiderivative, which we know to be the natural log of x. Now, normally, of course, we have a plus c, but this being a definite integral, we can ignore the plus c and make our lives a little simpler. Now, that being said, we also know that for our interval from 1 to b, x is always going to be positive. So in this case, we can drop the absolute value as well. Next, we can apply the fundamental theorem of calculus. The integral from 1 to b of 1 over x dx should therefore be the natural log of x evaluated at b minus the natural log of 1, which of course is simply 0. Our last step then is that we can evaluate the unbounded region by doing the limit as b approaches infinity of our integral. Well, in this case, we're looking at a simple limit to evaluate. We're looking at the natural logarithm of something that is approaching infinity. And the natural logarithm is an increasing function with no upper bound. So it will eventually also reach an output value of positive infinity. Thus, what we would say in this case is that this integral diverges. We would say that the unbounded region, in this case, has an infinite area. Thus, the integral diverges. That is the phrase that we will use here. Either the integral diverges, if it has an infinite area, or that the integral converges to a specific value. Now, the unbounded region diverging would seem to be somewhat intuitive. If we have a region that extends forever, it does seem intuitive that the area of such an unbounded region would be infinite. However, we will next look at an example of a function where the integral converges. And then we will talk about the difference between them. Let us consider now the integral from 0 to infinity of e to the negative x dx. E to the negative x is, of course, an exponential function. To sketch a quick graph of it, it is specifically an exponential decay function, which means as it extends to the right, we are looking at a similarly shaped region to what we saw in the previous example with 1 over x. Now, it is a similarly shaped region, but that does not necessarily mean that we will come out with the same result in terms of the value of the integral. So let us first do as we did in the previous example and replace the infinite limit of integration with a variable, b, and thus allow us to evaluate this integral by using a limit. So as before, we start with the antiderivative. This is simple enough to do. The inside function is negative x, which has a derivative of negative 1. So our antiderivative would be, again, e to the negative x, and then divided by negative 1 would result in negative e to the negative x. Once again, we can forego the plus c, knowing that we are about to apply the fundamental theorem of calculus here. The integral then from 0 to b, of e to the negative x dx would be equal to the antiderivative, negative e to the negative x, evaluated at b, minus negative e to the negative x evaluated at 0. Well, e to the negative 0 is the same as e to the 0, which is 1. So we have negative e to the negative b minus negative 1, or simply plus 1. Lastly, we can apply the limit. Ultimately, this is going to come down to what's going on with the negative e to the negative b, since the plus 1 term is unaffected by the limit. So we really need to look at what's going on with the first term. So what we have here then is negative e to the negative of a value that is approaching positive infinity. That means that we're going to be dealing with a larger and larger and larger exponent, but it will be a negative exponent due to the negative in front of this. So we're going to be looking at e to a negative, very, very large exponent. That should approach 0. Now, unlike the original function, it would approach 0 from underneath the axis because of the negative in front of the e to the negative power. But in either case, it is still approaching 0. So this first term will approach 0, and thus the entire limit comes out to be 1. What we would say then is that the integral from 0 to infinity of e to the negative x dx converges to 1. Saying it converges is very much like using the arrow notation that I have been using. It means that the area will approach 1. It will never actually reach it because the region never actually ends. It does keep extending forever. That's why we used a limit. B never actually approaches or never actually reaches infinity. It merely approaches it. It gets bigger, bigger, and bigger. Therefore, this will never exactly equal 1, but it will approach it. Now, the obvious question here, comparing this integral which converges with the previous example which diverged, why is it two similarly shaped regions? One of them has infinite area, while the other one somehow, while extending infinitely out to the right, somehow manages to have a finite area. The answer has to do with how they are approaching the x-axis. Some functions approach the x-axis more gradually, and some of them approach it more quickly. So the difference between whether it converges or diverges is a matter of the rate at which it approaches the x-axis. That is a phrase that in the previous lesson on L'Hopital's rule, we heard a couple of times. L'Hopital's rule was about examining the rate at which things approach. We will see L'Hopital's rule come up in a future example in this lesson. Let's consider, just to mix it up a bit, an improper integral that has a lower infinite limit. This time, from negative infinity to 0 of 1 over x squared plus 1 dx. So like before, we need to replace the lower limit of integration with a variable and allow a limit in front of the integral to let that variable approach, in this case, negative infinity. As before, we start with the antiderivative. Which is relatively straightforward. We should hopefully at this point recognize this integral 1 over x squared plus 1 as the derivative of, as the derivative of arctangent, so that the antiderivative of 1 over x squared plus 1 is the arctangent function itself. Once again, we can forego the plus c, knowing that we are about to apply the fundamental theorem of calculus. So our definite integral from a to 0 should then be the arctangent of x evaluated at 0 minus the arctangent of x evaluated at a. Well, the arctangent of 0 simply is 0. So we are left with negative arctangent A. Lastly, we can apply the limit. The arctangent function, remember that it is the inverse of the tangent function. On the left side, arctangent has a horizontal asymptote at negative pi over 2. Thus, as a approaches negative infinity, this function will approach negative pi over 2, but with the negative in front of the entire thing, we end up with pi over 2. And we can say then that this limit converges to pi over 2. We can actually get away with saying it is equal to pi over 2. However, for future lessons that will come up in this course, we should start getting in the habit of saying it converges, since it does not ever actually reach this. So our final conclusion would be that the integral from negative infinity to 0 of 1 over x squared plus 1 dx converges to pi over 2. Our next example will take us through a limit that is not quite so obvious in how to evaluate it. This time our integral is from 1 to infinity of 1 minus x times e to the negative x dx. First, as we've said before, we need to rewrite this by replacing the upper limit of integration with a variable. And then go through our 3 phases. The first phase being the antiderivative. So removing the limits of integration will allow us to focus on the function itself. This function does not immediately match any known formats, but it is a product. Now we could, I suppose, choose to distribute the e to the negative x. And while that would give us two separate terms, and the first would be easy enough to deal with, the second would still be a product. So in either case, we're looking at something that is going to require integration by parts. As such, I'm going to choose to leave the e to the negative x undistributed for now, but how you approach this is up to you. We know that e to a power both integrates or differentiates to the same level of complexity. So it does not matter which we choose for e to the negative x as, either dv or as u, but 1 minus x is a polynomial expression, and that would do best as u, where it can be differentiated. So I will let u equal 1 minus x, while dv is equal to negative e to the negative x dx. Du is therefore negative 1 times dx, while v is equal to negative e to the negative x. By integration by parts, then, the integral is equal to u times v minus the integral of v du. We have several negative signs here, but ultimately the 2 on the inside can cancel out and leave us simply with the 1 on the outside. Again, we can choose, if we wished, to distribute the negative e to the negative x, but at this point, we have reached an integral that we can readily deal with. And the purpose of this was to get the antiderivative, so I don't see a reason yet to distribute the negative e to the negative x, and thus I will leave it as is. As we already saw, the antiderivative of e to the negative x is negative e to the negative x, so that this cleans up one step further as plus e to the negative x. Now again, you can play with this as you wish to simplify it. At this point, I do see a purpose to distributing the negative e to the negative x, because when we do, we will have a negative e to the negative x term in front and a positive e to the negative x term later on, thus leaving us with simply xe to the negative x. So again, I did not distribute the e to the negative x just because I could. I left it until there was a reason to distribute it. This then is our antiderivative. We can now proceed to the fundamental theorem of calculus, where the integral from 1 to b of 1 minus x times e to the negative x dx is going to be equal to our antiderivative, xe to the negative x, evaluated at b, minus the antiderivative evaluated at 1, which will give us b e to the negative b minus 1 times e to the negative first, where it is not actually necessary to write the x equals 1 there. And this is our antiderivative evaluated at the limits of integration. so that now we can apply the limit to this expression. So our original integral from 1 to infinity of 1 minus x e to the negative x dx was rewritten as the limit as b approaches infinity of the integral from 1 to b of 1 minus x e to the negative x dx, which we now know to be equal to b e to the negative b minus e to the negative 1. It would perhaps be nice to be able to talk about each of these individually in terms of the limit. Because ultimately, it's only the first term that is affected by b approaching infinity. At this point also, I'm going to choose to rewrite it as b over e to the b. And there's a reason for that. Not that we can't deal with e to the negative b, but e to the positive b is certainly better. And, as you may have already begun to suspect, the numerator here is going to approach infinity, while the denominator also approaches infinity. Thus, we are going to need L'Hopital's rule in order to evaluate this limit. Now, of course, we do still have the minus 1 over e next to this, but for the moment, we need to focus on the limit. So I'm going to pull that out separately. And according to L'Hopital's rule, this should be equal to the limit as b approaches infinity of the derivative of the numerator over the derivative of the denominator. Which therefore breaks the indeterminate form because this turns it into 1, a constant 1, over something that in the denominator is going to approach infinity. Thus, this entire fraction is going to approach 0. So our limit approaches 0, and thus the integral converges to negative 1 over e. Remember that area below the x-axis is negative. And if we examine the graph of this function on the interval from 1 to infinity, we will see that the enclosed region does fall entirely below the x-axis. We will do one more example in this video, and that is to deal with a function that has both limits of integration being infinite. In this case, the integral from negative infinity to positive infinity of e to the x over 1 plus e to the 2x dx. We use a limit to replace the infinity either in the top limit or the bottom limit of integration But we cannot do both at the same time because we need different variables. Thus, we're going to separate this integral somewhere in the middle, somewhere in between negative infinity and positive infinity. We can pick any value we wish to separate this. But not only is 0 the most intuitive for being, well, basically in the middle, it is also intuitive because 0 is a very nice value to evaluate expressions at. So we're going to separate this integral into negative infinity to 0 of e to the x over 1 plus e to the 2x dx, plus the integral from 0 to positive infinity of e to the x over 1 plus e to the 2x dx. And then each of these can be rewritten using a limit. For the first one, since it's the lower limit, which is infinite, we will use a for the lower limit. And for the second integral, since it is the upper limit that approaches infinity, we will use b for the upper limit here. While this may seem doubly complicated, please keep in mind they are the same integrand, which means they have the same antiderivative. So once we do the antiderivative for one, we have it for both. Also, remember that we chose 0 as the separation point because evaluating these functions or any function at 0 tends to be very easy. We will need a quick substitution here in order to find the antiderivative. Namely, we will need the substitution that u is equal to e to the x. The idea, of course, being that e to the 2x can be rewritten as e to the x squared. Thus, du would be equal to e to the x dx. This will allow us to rewrite the antiderivative of e to the x over 1 plus e to the 2x dx as the integral of 1 over 1 plus u squared du, which, as we saw in a previous example, is simply the arctangent. Of course, one additional step, we do need to return to the original variable. So our antiderivative is arctangent of e to the x. And once again, we can forego the plus c given that we are about to do the fundamental theorem of calculus. Now, we have to do it twice because our limits of integration are different on each integral. So we have to apply the fundamental theorem of calculus to each integral separately. Let's do one at a time. Starting with the integral on the left side, from a to 0 of e to the x over 1 plus e to the 2x dx. This would be equal to the antiderivative, the arctangent of e to the x, evaluated at 0, minus the arctangent of e to the x evaluated at a. So we will have the arctangent of e to the 0 minus the arctangent of e to the a. E to the 0 is, of course, 1. And the arctangent of 1 is 1. Excuse me, is pi over 4. So we are left with pi over 4 minus the arctangent of e to the a. Separately, we have the integral from 0 to b of e to the x over 1 plus e to the 2x dx, which would therefore be equal to the arctangent of e to the x evaluated at b minus the arctangent of e to the x evaluated at 0. So we will have the arctangent of e to the b minus the arctangent of e to the 0, which, taking from earlier, the arctangent of e to the 0 is pi over 4. This actually cleans up rather nicely when we go to do our limits, which is our final phase. We now have our integral from negative infinity to infinity of e to the x over 1 plus e to the 2x dx, and that is equal to the limit as a approaches negative infinity of the integral from a to 0 of e to the x 1 over e to the 2x dx, plus the limit as b approaches positive infinity of the integral from 0 to b of e to the x over 1 plus e to the 2x dx, where each of these definite integrals we now have an expression for. So for the first limit, it is the limit as a approaches negative infinity of pi over 4 minus the arctangent of e to the a. And then we have plus the limit as b approaches positive infinity of the arctangent of e to the b minus pi over 4. Of course, the limits of the constants are themselves. So thus we have pi over 4 minus the arctangent of e raised to a power that is approaching negative infinity and then for the second limit, we have the arctangent of e raised to something that is approaching positive infinity minus pi over 4. And at this point, it's pretty clear to see that the pi over 4 and the subtraction of pi over 4 do cancel each other out, leaving us then with negative arctangent of e to a power that is approaching negative infinity. As e to a power is that is approaching negative infinity, as we get further and further out there, this should approach 0. In the second term here, as e is raised to a larger and larger and larger power, this should approach infinity. The arctangent of 0, as something approaches 0, arctangent will also approach 0. On the right side, as the arctangent moves further and further to the right, as its input approaches infinity, arctangent will approach pi over 2. So that altogether, this approaches pi over 2. Thus, we can say that the integral from negative infinity to infinity of e to the x over 1 plus e to the 2x dx converges to pi over 2. In the next video, we will look at improper integrals, where the limits of integration are not infinite, but rather the function has an infinite discontinuity in the interval.